Hey physics friends, today I'm going to be talking about how do you send a ray through a lens, specifically a prism. We're going to be sending a ray through 3 different blocks today, and we're going to be using Snell's law. So for this today you're going to need a pencil, and it has to be really sharp. In order for this to work well, it's got to be sharp. So the first thing I want you to do, sharpen your pencil. Number 2, we're going to need our compass. Number 3, we're going to need our a calculator. And number 4, we're going to need a really nice protractor. These are the tools of the trade that we're going to be using today to send a ray through a block. So these are big acrylic blocks that I've traced. I borrow them from the university every year, and it's literally, I set it right down on top of here, and then I trace it out, draw a ray. You predict how it goes through it, and then you put a laser next to it and see if it actually goes through, and see how good you did it and how accurate you can be. So I think this is the one I'm going to have you do. But what I'm going to do is do another example. I'll do an example right here of something maybe similar. So here's your first example. Here's my incident ray coming in here into this block. Now this block has an index of refraction of 1.49, and this is air, so it has an index of refraction of 1.00. So the first order of business is to plug it into Snell's law. So Snell's law, N1 sine theta 1 equals N2 sine theta 2. So we're going from air. So this is what we're going from, and this is what we're going into. So we're going from air. Now we have to find the angle of incidence. So basically, what you're going to do is, first order of business, we got to find this angle of incidence here. So we're going to construct a normal, and you have to be really good about this, because you're going to start doing calculations with a number that you measure, and you're only as good as your measurement. So I'm going to make my normal actually over on this side, very lightly, but very nice, sharp, crisp lines. And I'm not going to make it too dark, because we might end up getting a lot of stuff going on here. So I'm going to make it nice and light. See how fine that is? And then what I'm going to do is I have to measure the angle of incidence. Now the angle of incidence is this angle right here. So this is where I'm going to have to get my compass out. Now the protractor. So what I'm going to do, I have to make real sure, and I actually made my paper a little bit longer so I could make sure that I was lined up the best I could on it to get a good reading. So I make sure a few things. Number 1, I make sure that this goes through the 90. I make sure that this mark down here goes through my line, and I want to make as best I can. And I'm going to measure my angle. It looks to be 35, 36, 37.5. I always go one more than what. These are marked off every 1 degree, so I'm going to estimate that final decimal point, so 37.5. And now it's going to be going into the block, 1.49 times the sine of theta 2. So now here's where your calculator comes in. You have to make sure that your calculator is in degree mode. So you hit the mode button and you look down and make sure that it's in degree. Mine's in degree mode, so that's okay. So I'm going to take 1 times the sine of 37.5, and then I'm going to divide by 1.49, and then I take the inverse sine of it, second function sine of my answer, and I get 24.1 degrees. Now, remember, theta 1 is on this side of the normal, so that means that theta 2 has to be on the other side of the normal. And this is a big mistake I see. When I see people doing this, I see it all the time. You put the angle on the wrong side of the normal. Theta 1, since it's on the left, that means that theta 2 is going to be on the right. Then I have to accurately use my protractor again. Make sure the 90, make sure this is here, 24.1. So here's 25, 24.1, right around there. So then I draw my ray through here, and I make sure I draw it straight until it hits another boundary. It's going to go, I draw it straight until it hits the other side of my prism. And now I repeat the process all over again. I continue drawing rays until it hits the other side. So this one, my guess is it's probably going to bend through and it's going to hit somewhere over here. Step 1, draw the normal. Step 2, measure theta 1. Step 3, plug it into Snell's law. If you get an error, you may end up with error. That means that it doesn't go through this side, it internally reflects. So you may get some sort of reflection on the inside, and they call that total internal reflection. So on my case over here, this goes through, I'll draw my normal, and you may choose to use your protractor to make your 90 degrees, but I don't ever trust it. Believe it or not, your compass is much more accurate in doing this stuff, and it's real simple to do when you're doing this if you do it right. Now, believe it or not, my theory is that this side is parallel to this side, and this is that whole alternate interior angles. So my guess is that this angle right here equals this angle right there by alternate interior angles. So because this is 24.1, this should be 24.1. I can just double check it with my protractor, and sure enough, it looks really close to 24.1. So now I'm going to run it through Snell's law. N1 sine theta 1 equals N2 sine theta 2. So it's going from the block into air. So N1 is 1.49. Another big mistake that I see a lot of times is people always put 1 in for N1. That's not always the case. It depends what it's going from and what is it going into. In this case, it's going from the block into the air. So sine 24.1 equals N2, it's going into air, times the sine of theta 2. Now, just because I'm a little bit of a math geek, 1.49 times the sine of 24.1, and I divide by 1, and I take the inverse sine of that. 50 bucks says it's going to be 37.5. So inverse sine of my answer, 37.5. There's a little bit of cool symmetry when you've got like a rectangular prism here. It came in at 37.5. I've got alternate interior angles, and then this goes out at 37.5 degrees. So I put this guy here. I may have to elongate my paper in order for this to work. So I just have another piece of paper underneath my paper in order to do that. So here's 35, 36, 37.1 right there. Like that. And remember, theta 1 is on one side of the normal. Theta 2 has to be on the other side. So, just so I can kind of reiterate, I've got my incident ray. I've got my transmitted ray, or my refracted ray, and then I've got another refracted ray coming out. So when I put my laser up to this, I bet it goes right along my pink line here. And if I did a good job, you'll be right on. You know, if you didn't do a good job, if you've got a dull pencil, a floppy compass, or bad measuring habits, you're not going to get it to come on to work out very well. I'm going to do one more for you, and this is a ray that's going through a triangular prism. So here's your ray. I'm going to do a practice one or an example one right up here. Maybe I'll actually do it down here. So here's mine coming in. So incident. So again, order of business number 1, find the normal. And we're going to plug it into Snell's law. So take my compass. I'll make one on one side, one on the other. Open my compass up. And take your time with these. In order to be accurate, you have to do a good job in measuring and drawing. So here's my normal. So I'm going to measure this angle. And this angle comes out to be 60.5 degrees. So it's on this side of the normal, and it's 60.5 degrees. Now, theta 2 is always going to be on the opposite. So I run it through Snell's law. So N1 sine theta 1 equals N2 sine theta 2. It's going from air. So it's going from air. It's going into my block. And I solve this for theta 2. So I pull out my calculator and I go 1 times the sine of 60.5 divided by 1.49, and I take the inverse sine of it, and it comes out to 35.7. So now I go 35.7 degrees on this side of it. So here's 35, 36, 37.5 right there. Draw my line. Make sure you twist your pencil as you're drawing your lines. And now we repeat. So again, I have to draw my normal with my compass. I mean, it looks like it's hitting at a right angle, but we'll see. I mean, we may only have a few degrees here. And we'll open up my compass. We'll go on this side. Yeah, there we go. So here's my normal. So here is theta 1. This little tiny sliver of an angle right there. And it's pretty big, actually. It doesn't look very big, but we're talking it is 7.6 degrees, I estimate it. So when I run this through Snell's law, so I'll go N1 sine theta 1 equals N2 sine theta 2. N1, it's going from my block, 1.49. And it's going into, the theta 1 is 7.6 degrees. N2 into the air, sine theta 2. Now this one's not going to be as nice as the other one. It's not. There isn't going to be symmetry here. It's not going to be 60.5. It's going to be something else. So calculator time, 1.49 sine of 7.6 divided by, well, actually inverse sine of that. It should be 11.4 degrees. So again, make sure you pick the correct side of the normal. So this one's on the top side, this one's going to be on the bottom side. And it's got to be 11.4 degrees. So get my right here, measured up 11.4. So right there to right here. Boom. And then pull the laser over and see how good you did. If you did a good job, sharp pencil, good compass, careful measurements, good math, it will all add up to tracing that ray through very well.